Hello, this is Dr. Rashmi Deshpande on my channel RT Physics. This is the course on atomic and molecular physics and it is fifth lecture of the series. We are discussing hydrogen atom problem on the basis of quantum mechanics. Today we are going to discuss the orbital angular momentum of electron in hydrogen atom and we will also discuss orbital magnetic moment of the electron. In the beginning, we will start with the orbital quantum number and angular momentum of the electron. We are going to derive the relation between these two, that is orbital quantum number and angular momentum of the electron. So let us start with the R equation. The equation for radial part of the wave function psi of hydrogen atom that we have derived in the previous lecture is rewritten over here. It is 1 upon r square d by dr r square dr by dr plus 2m upon h cross square e plus e square upon 4 pi epsilon 0 r minus L into L plus 1 upon r square into r is equal to 0. When we had derived this particular differential equation, at that time we have just taken this L into L plus 1 as a constant to equate both LHS and RHS, and at that time we had said that what is the meaning of this L into L plus 1 constant, what is the significance of it, that we would be discussing later. So now we are going to see what is the significance of this L into L plus 1. So as I have said earlier, we have rewritten the R equation and let us call it equation number 1. Now in this equation, capital E is total energy. Okay. Total energy of the electron, which is a sum of kinetic energy and potential energy. Now the kinetic energy term is again made up of two parts, that is radial kinetic energy and orbital kinetic energy. If you consider the motion of electron around the positively charged nucleus in the hydrogen atom, then it is having motion along the position vector, that is r, small r, and also it is having the angular motion. So therefore it is having the radial kinetic energy and orbital kinetic energy. So let us denote it by Ke radial and Ke orbital. The potential energy of the electron, as we have stated in the beginning, it is Coulomb potential, that is electrostatic energy given by Vr is equal to minus E square upon 4 pi epsilon 0 r, where small e is the charge on the electron and small r is the radial distance of the electron from the nucleus. Hence the total energy of the electron we can write as addition of kinetic energy radial plus kinetic energy orbital, that is this is the total of the kinetic energy, and plus potential energy V. So we have substituted here the potential energy term and then we are going to substitute this capital E in our initial equation. Okay, so if we substitute for energy, that is capital E, then this minus E square upon 4 pi epsilon 0 r will get cancelled out with the E square upon 4 pi epsilon 0 r, and so therefore we get this term, that 2m upon h cross square kinetic energy radial plus kinetic energy orbital will only remain, and because we have substituted for capital E this particular term, this negative term has got cancelled out and this is the remaining term. Okay, multiplied by r, this is equal to 0. Now if you look at this particular equation, see each term except this term, all are dependent upon the variable r. Kinetic energy orbital, because it is because of the orbital motion of the electron, where the angle of the electron is changing with respect to z-axis, as well as with in the xy plane it is changing. So the kinetic energy orbital, it involves angle. So this is the only term which is not dependent upon r. Okay, so if we want this equation to be representing a equation in r variable, then we have to get rid of this term. Now how can we get rid of this term? So this equation will contain only r if these two terms are equated, means because this is the only negative term. Okay, so if this kinetic energy orbital multiplied by 2m upon h cross square, suppose if it is equal to this L into L plus 1 upon r square, then these two will get cancelled and only the terms containing r will be there in the equation. Okay, so kinetic energy orbital we are equating with this L into L plus 1 upon r square. Remember that 2m upon h cross square factor was there. So if we shift it on the RHS, it will become h cross square upon 2m. Okay, so we have multiplied that L into L plus 1 divided by r square with h cross square upon 2m. Okay. Now the orbital kinetic energy of the electron is given by this half mv square, where v orbital is the velocity of orbital motion. So this is our general formula for kinetic energy, that half mv square. Okay. Also we know that the angular momentum of the electron is given by mvr. Okay, where mv will be the linear momentum. So angular momentum is mvr. So this velocity is the orbital velocity. So I can write this v orbital is equal to L divided by mr. Now substitute for this v orbital in the expression for kinetic energy and I get this L square upon 2mr square. Okay. In the previous slide we have seen that the kinetic energy orbital was equal to h cross square into L into L plus 1 divided by 2mr square. Now here from equation number 7 we have obtained that kinetic energy orbital is L square upon 2mr square. Okay, so from equation number 7 and from equation number 4 we have got this equality. Okay, now if you look at the two sides of this equation, the denominator will get cancelled out. Okay, so what will remain? L square is equal to h cross square into L plus 1. So therefore I can write L is equal to h cross into L plus 1. This is nothing but the electron orbital angular momentum, magnitude of the electron orbital angular momentum. So from this equation we can see that the orbital angular momentum of the electron is quantized and its quantization is determined by this quantum number L. So therefore this quantum number is called as orbital quantum number. So we have seen in the previous lecture that L can take values from 0, 1, 2, 3 up to n minus 1. So therefore correspondingly we can find out what are the different possible magnitudes of the orbital angular momentum. So equation number 8 proves the quantization of magnitude of the orbital angular momentum of electron in hydrogen atom. Now we are going to discuss what is the orbital magnetic moment. Okay. Now in this particular discussion we are actually drawing a similarity between the moving electron and the current carrying loop, and this is equivalent to a magnetic dipole, and so that is why it has a dipole moment. So that let us start the discussion. Now the hydrogen atom has one electron revolving around the nucleus. It can be considered as a tiny current carrying loop because a charge moving in orbit is equivalent to, is like a current carrying loop. Charge E flows new revolutions per second in an orbit of radius r. Okay, uh, please remember that current carrying loop we are calling it. It is because it is the charge which is flowing, and charge per unit time is nothing but current. So here the electronic charge, that is charge E, is flowing with frequency nu. It flows new revolutions per second, means its frequency is nu. Let's remember that this is Greek letter nu, though it is looking like V. Okay. And what is the radius of the orbit? It is r. Now a current carrying loop has magnetic field like that of a dipole. Okay. We know that a changing electric field produces a magnetic field. So similarly, this current carrying loop, which is produced by the moving electron in the orbit around the nucleus, it is, we are considering it to be like a tiny magnet. Okay, so it will have a magnetic moment associated with it, which is denoted by mu bar. Please look here, this is vector mu bar. Okay, so this dipole moment has arisen because of the orbital motion of the electron. So that is why it is called as orbital magnetic moment. Now how to calculate the orbital magnetic moment? So for that, let us consider the Ampere's theorem. According to Ampere's theorem, the magnetic moment is equal to current times area enclosed by the loop. Okay. Now here area enclosed by the loop is nothing but the area of cross section of the orbit. Let us denote it by capital A. So this magnetic moment will be current times the area. Okay. And now what is the current? Current is equal to charge flowing per unit time. Charge is minus E of the electron and flowing per unit time. So charge per unit time, that is nothing but charge multiplied by frequency nu. So the magnetic moment will be equal to, if I substitute for I, this minus E into nu multiplied by area of cross section, that is pi r square. Okay. Now when the electron in hydrogen atom is moving in an orbit of radius r, then its linear speed is v is equal to r omega. Okay, and omega is nothing but 2 pi nu into omega is 2 pi nu. Okay, so v will be equal to 2 pi nu into r. So magnitude of its angular momentum is given by L. The magnitude of angular momentum is, orbital angular momentum is L, which is equal to mvr. V is velocity. So that will be equal to m into 2 pi nu r multiplied by r. Okay. So please make this correction. This has to be nu because it looks like V. So I will, so that there should not be any confusion, I will just make it nu. Okay. So there should not be any confusion. Sorry. This is nu, this is v. Remember, this is velocity, this is nu, that is frequency. Okay, so m into 2 pi nu into r. So multiplied by r, because this r is there, and here also it will be then 2 pi m nu into r square. Okay, taking ratio of mu and L. See, we have obtained earlier the expression for mu, okay, in the previous slide. So take a ratio of this mu and L, then it will be minus E into nu multiplied by pi into r square. This is current I multiplied by area of cross section of the orbit divided by the angular momentum, that is orbital angular momentum, 2 pi m nu into r square. Okay, so nu will get cancelled, r square will get cancelled, pi will get cancelled. What you have? Minus e divided by 2m. Okay, so the ratio of orbital magnetic moment to the orbital angular momentum magnitude is minus e divided by 2m. Remember, E, that is electronic charge, is a constant. M, that is electronic mass, that is again a constant. So the quantity minus E divided by 2m is also a constant. This constant is called as gyromagnetic ratio. Okay, so the ratio of orbital magnetic moment to orbital angular momentum of the electron is called as gyromagnetic ratio for orbital motion, and it is given by minus E upon 2m. The minus sign shows that mu bar, that is the vector magnetic moment, is in opposite direction of vector angular momentum. Okay, so if we write it in vector notation, then mu bar is equal to minus E divided by 2m into L bar. So vectorially we can say that mu bar vector and L bar vector are in opposite directions. Now we have determined the magnitude of orbital angular momentum, that is h cross under root L into L plus 1. So therefore in magnitude we can write that magnetic moment is minus E upon 2m into h cross under root L into L plus 1. This quantity minus E upon 2m h cross, this has dimensions of magnetic moment, because under root L into L plus 1 is a constant which is determined by the orbital quantum number L. Okay, so therefore this minus E upon 2m into h cross, it has dimensions of magnetic moment. So in other words, we can say that this magnetic moment is in the units of this particular quantity, which is called as Bohr magneton, and it has a constant value 9.274 into 10 raised to minus 24 ampere meter square, and it is a fundamental unit of magnetic moment in the atomic systems. Means many a times magnetic moment is expressed in units of Bohr magneton, and it is denoted by mu b. So in terms of mu b, the orbital magnetic moment can be written as minus mu b under root L into L plus 1. This notation mu L is used because L denotes that it is the orbital magnetic moment. Okay. So that's all for the today's lecture. Thank you very much.